Okay, now recording. Hello, everyone. Welcome to the programming and debugging lecture. Neil couldn't be with us today. He's traveling, so he asked Norella and me to co-host. That's it, short and sweet. Nicolas and Henk will be guiding us through this recitation. Take it away.
Okay, thanks, Luciana. We have the very challenging task to explain you a lot today, which is about microcontroller programming and debugging, which is a week course that we will try to give in 1 hour. So it will be quite challenging. So we'll keep the very basic. We won't make it too hard, too complicated, and our goal is not to duplicate the coming course about AMP programming. So our goal will be to be very practical about how you can actually program a microcontroller and what you can do when things are going wrong. So first, we'll start speaking about the different microcontroller we use. We have several families we use in Fab Academy. There are plenty of microcontrollers you can actually use for your project, but we try to keep a short list for the microcontroller you can actually use for your project. The basic one are the ATtiny, which is the smallest one. I will explain a little bit after that. They are very small. They are very capable actually for the size and for the memory they have if you use them properly. SAMD are a bit more powerful. They can do 30-bit operation, do USB and so on. RP2040 are our new favorite. These are the microchip, Raspberry, microcontrollers, much more advanced. They really are like, let's say, small computer, and ESP32 when you need actually wireless transmission, Bluetooth or Wi-Fi. So the ATtiny, as I said, are very small. They are low cost also, and they are programmed through a unique pin. So they are very small chips you can put in small project, I will say. They have a package which is really small too on your PCB, and they are only 8 bits. They can go from 1 to 20 megahertz, more or less, and they are very versatile. They have a lot of analog capabilities, PWM, and different protocols. I will talk a little bit more later. They are programmed through a protocol which is called UPDI. I won't go too much into details about the protocol to program your chip, but to put a program inside your chip, you need to actually send the program to your chip, and one of the big advantages of the ATtiny is only use one pin to do so. And for every microcontroller I will talk about today, you have a Adrian board, which is already ready for you to test, which is the Adrian, that was the first project, and then Adrian created some other cards, other boards for the other microcontrollers. The other one is SAMD. They are a little bit more capable, 32 bits. Programming them is a little bit more complicated, but what you actually do is usually to just put a small program in it, which is called a bootloader, and that will let you send program then after that through the USB. So only the first operation to send that bootloader to the chip is the difficult operation. Then you have the RP2040 that we usually use on Chow boards. We also use the Raspberry Pi Pico, which is basically the same with much more pins. So when you need more pins, use the Raspberry Pico, otherwise use the Chow RP2040. The big advantage is the bootloader is already on it, and you can't erase it. So even though you make some mistakes or some dumb things, it will always keep running because there is the onboard hard-coded UF2 bootloader. So you can't really break it, actually. So that's one of the advantages of the RP2040. They are much more capable, 32 bits, 133 megahertz, but you can easily overclock them, so you can do a lot of operation and calculus on those microcontrollers. They are much more capable than ATtiny, for example. It also usually means that they will use a little bit more power, so just keep in mind that if your project needs to run on battery or something, you probably need smaller microcontrollers. ESP32, C3 or S3, or now even C6, I think, are also very capable microcontrollers with a lot of power, and moreover they have like Wi-Fi and Bluetooth, which make them suitable if you need wireless operations. There are other microcontrollers, but I won't go into details for those because we don't really use them in the network. They are not part of our inventory. Once you have chosen your microcontroller, you need to use a language. You have to explain your program and how you will program your chip. And for this, you will have to choose a language, a programming language, to explain what you want to do on your microcontroller. So for this, I've set up a small website. On my website, I've put sort of documentation page, then you can go to. The link is inside the recitation. And on this page, you can have a quick look on all the different languages you can choose to control your microcontroller. I will only focus on RP2040 because it's one of the most used in the network, and we are pushing it a little bit. You can all I will explain will more or less be suitable for the ESP32 microcontrollers too. If you use smaller microcontrollers like ATtiny, you can't use all this programming language, but I will go a little bit into details now. On RP2040, you can use, I just put 8 different languages, which is already a lot, much more than you will ever need. So I just put it to be more or less complete. The first one, and one we push a lot, is MicroPython. MicroPython will let you have a very small Python code on your microcontroller, and will be able to interpret your instruction while it's operating. So it's called it is called an interpreted language. So it's not compiled. You can send instruction while it is running, and it will make it work. So it requires quite a lot of power to do so, because it has to understand all your lines of code while it is running. So it's not the most efficient way to program a microcontroller, but that's one of the easiest way. For me, that would be an issue, actually, to use too much power to do the same thing. But now that we have the PIO, which is a special peripheral from the RP2040, there is a good balance using MicroPython with PIO. I will go a little bit more into details with MicroPython today. The other one, very famous one, we use it a lot into the network, and it will work for all the microprocessor we use, is C and C++. So that's I will say the basic language when you have to program anything on a computer, on a microcontroller or anything, and you have to do it efficiently. C or C++ is a compiled language, so it means that your computer will actually translate all your code in machine code. Then you will send it to the chip, and then it will run on it. So it doesn't have to do all the effort of interpreting all your lines, and it will reduce the actual amount of power and computational power you need on your computer, on your microcontroller. Another one is CircuitPython. CircuitPython is basically the same as MicroPython. The use of CircuitPython is a little bit different. It's even easier than MicroPython, but it's a little bit less efficient. So I still recommend to use MicroPython unless you actually need to go with very easy things, or if you need specific libraries that are available in MicroPython, because they provide quite a lot of very good and advanced libraries. So that's, I will say, the less efficient way you can use a microcontroller, but you can do quite advanced things quite easily. So that could be a good solution if you really want to start with an easy thing. C++, not using Arduino, because Arduino is a big library that will ease a lot of things for you, but at the price of doing things a little bit less efficiently than real pure C on C++. So if you want to do real pure C, C++, to maximize and to very optimize your code, you can go with the C and C++ Pico SDK. So you just download the SDK from Raspberry, and then you can use really raw C or C++ for your microcontroller to program it. Another one, I just put it for the fun, because I actually never used it. I know you can do some project with it, but that's not the option I would recommend. But you can actually use JavaScript on your microcontroller. For this, there is Kalima.js that will let you do this. So it's the same as MicroPython. It's an interpreted language. You can just launch a small OS which is able to understand JavaScript, and you can run JavaScript code on your microcontroller. The only use, I think, that can justify using JavaScript on a microcontroller is if you want all your project to be in JavaScript. If you want everything to run in JavaScript with Node.js, or on your browser with JavaScript, you want JavaScript everywhere, you don't want several languages for different things, you might use JavaScript on a microcontroller. Rust, that was my assignment 1 year ago during the instructor bootcamp. I tried to make a Rust run on the RP2040. That's the real new competitor with C, C++, so I will compare it to this one, to the Raspberry Pico C, C++. You can actually make Rust code run on a microcontroller. It works, but it's pretty difficult to compile and to send to the microcontroller, so that's not really an option I would recommend. I just tested it, so I put it here. But the fun of it is that since I have tested it on the RP2040, I don't use it on RP2040, but now I use it for my everyday computer programming. So I use it on a real computer, not on microcontroller, but because I tested it for microcontrollers. You can even program your microcontrollers in Go, which is the Google language. But once again, that's not something I really recommend, because Go was made to ease the use of serial processor. The good thing is that RP2040 has two cores, so you can theoretically make them run both, using both for running your code. But the implementation of Go for microcontrollers, as far as I know, are not very well implemented, and so you can't really use both your code, so that's not really a good option either. And if you are geeky enough and adventurous enough, there is still the assembly. It's really you write the computer code that only your chip will understand. So it means really to speak your actual microcontroller language. And that's something, of course, which is very difficult to do, but then you can optimize to heaven your code if you are adventurous and geeky enough. So that's if you want to really speak a machine language. Also know that if you do so in assembly, it means that you have to know your chip perfectly, and your code will not be the same for RP2040 and for ESP or ATtiny or so on. Your language will vary depending on your actual chip. So you really have to know your hardware very well. We don't want to frighten you today. We really want to start with the basics. So what I did is to explain the very basic of MicroPython, how to program a chip with MicroPython. And all the equivalent is also available on the page about Arduino. Let's also know that this page is not very complete. I didn't fill already the Pico SDK, for example, because I didn't have enough of time. But on this page, you can find small examples for every different solution except the Pico right now. So on MicroPython, if you click, you will have the explanation about how to install your MicroPython environment. For every language, I created too long, didn't read, so a very small section to explain you how to install it. If you want more detailed explanation, it's available on the C Studio website. But all you have to do, basically, is having Python on your machine and install what's called Thorny. And you launch Thorny, and you can just put a small piece of code inside your microcontroller, and then you have Python on RP2040. Once you have that, you will start writing actual code that you will be able to send to your chip and make it execute. So I will go through a set of small examples and small pieces of code, and I will, for every small piece of code, I will show you the simulation I did on Walkwi. So one thing you can do if you don't want to actually use your microcontroller because you're not with the hardware in your hands, you can actually simulate it. And for this, Walkwi is a super helpful website. You can simulate all your stuff on it. As far as I know, there are not Xiao RP2040, but there is the Raspberry Pico, which is exactly the same. So you can just simulate it on a Raspberry Pico on Walkwi, and it will work just great. So what I will do every time is just make a LED blink. That's called the Hello World. Hello World is with any microcontroller, the first thing you make sure you are able to do is blinking a LED. If you can blink a LED, that's a very good start. It means that you can talk to your microcontroller and make him do what you want to do. So for this very first example, I make something very simple. I just did what's called a while true loop. It means that it's a loop that will go forever. While true means that you do something as long as the condition is true, but the condition true is always true, so it means forever. You go through that loop, you just toggle a LED. The first thing you have to do is to say that the pin that you want to write on it is an output, it's not an input. You don't send information to it, you want it to be the information, which is it on or off, and that's all that only a small line does. And then you go through an infinite loop, and you say, forever, what you do is you toggle the LED. If it was on, you put it off. If it was off, you put it on. And then you wait half a second, which means that that loop will approximately take 1 second. Every 1 second, you will have a on, off, on, off, on, off. And so you just can click on the simulation, and then you will see it just blinks. Note that for my simulation, I put an LED just to make it more clear. So in the code I use pin 0, while in my code in here I use pin 25, because on the Xiao, the small blue LED which is inside the Xiao board is pin 25, so I just adapted the pin. I could also have used the pin 25 in here to make blink this LED, but it's very small, so I had to zoom very deep to make it visible. And for every small piece of code here, I put a link, so you can actually click on it and play with it on Walkwi. You can change if you want to change that 1 Hertz and you want to make it blink slower, for example, just put 0.8 and then you simulate it and it will go a little bit slower. So I really encourage you to first play on Walkwi before starting to send actual code to your microcontroller. Yes, I want to leave the page. So that was the easiest example I can think of. I will do now the same, but only several times, and then I will stop. I don't want to do it forever. And what I do is I put my LED as an output, and I put a number 10 in a variable, which is A. So A is now 10, and then I will loop like the previous example, but every time I loop, I will make A 1 less. It will be A will be 10, and then 9, and then 8, and then 7, and so on. And I will check every time that A is still bigger than 0. If it's not, if it is 0, it will stop. So it means that it will go into the loop 10 times, and after 10 times, it will stop. And as I toggle my LED every cycle, it means that it will blink only 5 times, and then it will stop. So let's see how it goes. A is 10, then 9, then 8, and so on. And after 5 times, you see that the program stopped. And interestingly, you see that you get now a terminal you can type off, because the processor is done with the code in here, and now you can type directly MicroPython in it, directly inside the terminal that you get in here. like every time, you can click on the walkway example and play with it if you want to test a little bit further. You can do exactly the same with the for loop. So far we used a while loop. It means while a condition is true, and then you can do exactly the same with a for loop, and that for loop will go in range 10. It means that for every time we are in the range of 10, it means for 10 times, for 1, 2, 3, 4, 5, and so on, you will toggle the LED, sleep 0.5 seconds, and go to the next. So after 5 blinks, you should end your code in here, and then you can test it, and it will be 5 times, and then it stops, and you get back your terminal. Okay, so exactly the same code, but with a for loop, because you say for something that you don't use, you can make a variable in here, and I will show you how just after that. But you just range from for 10 values, and you go to that loop 10 times, and then you stop. As usually, you can click, and then you can play with it. What you can do while programming is creating a function that will ease your code. Instead of writing every time the same thing again and again, you can create a small function that will be responsible for some code execution, and then you can use it in another part of your code. And I really encourage you to do so, to write in a modular way, which means you create some small section of code which are function, and you use them. They are specialized in what they need to do. So what I'm doing here is still with a for loop, but with a definition of function. And what I do is I will put my LED on, and I will say for I in range 5, so it means for I that will go to 5 values, you will blink the LED, and I will explain what is blinking a LED. And that I do in here, which is the function blink a LED, which gets an argument, which is the number of times you must blink the LED, and that number of times you will blink the LED. And you see that the code is for the number of times which is in range time, you put it on, you sleep 0.2 seconds, you put it off, you sleep 0.3 seconds. So it will make it blink shortly, and it will do it the amount of time you ask it to do it. So what I do is I will go from I in range 5, you will blink the LED, so we'll blink 1 time, 2 times, 3 times, and so on, and then you sleep during 2 seconds. Let's see the result. I run the simulation, then it will blink 1 time, then 2 times, then 3 times, then 4 times, and then up, it's done. Maybe you have noticed that it didn't blink 5 times, and I will use it voluntarily a little bit later. You can also use arrays, which is a very common way to program things sequentially. You define an array, which is a table in which you put several numbers, 3, 7, 2, 5, 1. I just pick random numbers. And then I will say, you will use that function, which is blink x times, and you will go for I in values. So now it won't go from 1, 2, 3, 4, 5, and so on. You will go from the values that are in the array in here. So the first time you will blink 3 times, the next time you will blink 7 times, then 2 times, 5 times, 1 time. And then between every number of blinks, you will sleep 2 seconds to see clearly the difference. So let's go to it. It will blink first 3 times, 3, then 7 times, then 2 times, then 5 times, then 1 time. And as usually, you just can click on the walkway project to play with it. If you want to play with other arrays, other size of arrays, and so on, you can change the code. So I really encourage you, if you never have you never programmed, to test it on walkway. Another very important concept that you always use when you do programming is the if-then-else. Actually, I didn't said it yet, but using loops and if-then-else is the very definition of what an algorithm is, and that's why we consider that the first actual algorithm was written by Ada Lovelace even when a computer didn't exist, she was the one that really wrote the first algorithm, the first explanation using loops and conditional branching that I will explain right now. So a conditional branching is you verify a condition, and if the condition is true, you go to a section of code, and if the condition is false, you go to another section of code. And that's what I will do in here. You still put the LED as an output. The blink LED definition function is still the same. And now what I will do is I will go in range 5, and if the number is divisible by 2, which means it's an even number, you have to blink the LED 2 times, and if it's not, it means that it's an odd number, you will blink it only 1 time. So let's go. It will start blinking 2 times, then 1 time, then 2 times, then 1 time, and then 2 times, and so on and so on, until the for loop is finished, and then it will just end the program. Okay, so that was the very basic. For all I just explained, you have the very equivalent that you can use actually in Arduino, which means in C. You can go here in C, C++. So I just put exactly all the same codes. You can do an infinite loop using C, so that's exactly the same code, and I didn't actually remake new videos because the videos are exactly the same, except that the code in here will be C code, but the result will be exactly the same, but now it's written in C instead of being written in MicroPython, and this you can use in Arduino. But you can also play with it on Wokwi in C, so you can either play with C, C++, or with MicroPython. So you will find all the example I just go through in the C equivalent. So if you want to program in Arduino and C, C++, all the examples I just show are also available on my webpage. Now, the very big new things, I would say new, we already play with it since 1 or 2 years, but on RP 2040, there is a special module which is called a PIO, which is a programmable input-output peripheral. And this you can program in a very assembly way. You remember I explained what is assembly code, so it means that you have to speak a much more machine language, but you can go through every instruction very smartly and very optimized way. So this is the very naive and I will say stupid code to blink a LED on RP20 PIO. What I do is just I set my pin on, and then I will do nothing. Each time you see this, it's lose time. Do nothing during 31 operation, then do nothing, and then do nothing during 31 operation. And why am I putting all those knobs? Why do I want to lose so much time? It's because otherwise your eye will see nothing. It will be too fast actually. It's so efficient that you have to lose as much time as you can between putting the pin on or off. So for this, I just set the pin on, then I wait as much as I can, then I put it down, and then I wait as much as I can, and then I will loop through this, and that will make my LED blink. See that when I launch this PIO, I do it at the frequency of 2 kilohertz, which is already the slowest actually code you might execute. You can't really go any slower. So for all this, I make the code run as slow as I could. And you will see that I have 32 operations because that's the maximum operation you can put in a PIO. And that's the result. I just put PIO, so it means now that my main core won't be responsible for blinking the LED. Another specialized peripheral will do it for me, so I will be able to do other stuff on the main core, which is the very interesting things. I will launch the simulation, and you will see that you directly have access to your terminal, because actually your main core is not busy. What makes the LED blink is the PIO, so you can use your main core for other stuff, which is very interesting. You can do a little bit smarter loop. Instead of just losing time, you can also have an equivalent of for loop. You just set it a little bit an equivalent of for underscore in range 31. And you can do something like that, but inside PIO, and so you can get the same result, but in a much smarter way, which means that you won't use all your PIO to do the same thing. And you see that you will blink even slower. Okay, but so PIO lets you do very fast things, very efficient things, use your capabilities very fast. And so it's not always easy to see what it's actually doing, and it's not doing it on the main core. So that's where we will start playing with debugging. So I will introduce the very basics of the debugging, but I will remain here in the virtual world on my computer, and then Henk will explain a little bit more about the actual instrument, physical instrument that you can use to electrically measure things. So I remit exactly the same things, just set the pin on and then set the pin off, and even though I'm on a very slow frequency in here, if I just launch that code, you will see nothing. You will just see a LED which is half blinking. You will just half power, because your eyes unable to see something changing 2000 times per second. So just to make it more clear, actually the LED will blink 1000 times per second because you have 2 instructions to do so, but then you will see nothing. And then what you do is you connect a logical analyzer, which is a specialized device that will look your pin, that will record what's happening on your pin, and then you will analyze that signal on your computer or your logical analyzer to see what was actually happening. So it lets you see what was too fast to see, actually. So I will launch it. If you do so, the LED, you don't see what's happening. It's blinking, but you don't see it. And if you do it on simulation, when you stop, you get a new file in here that will be downloaded automatically. And then you can open that file, for example, on PulseView, which is, I think, available on every system. You can't really see me opening the file, but then you will see what was happening on your pin, and then you can analyze it. And then you can, for example, measure what was the time between 2 blinks. You see that the signal is going on and off and on and off. And then you can actually measure it was 1 kilohertz, which is exactly what was expected. And it took only 1 millisecond to go on and off. Okay, but your eyes is totally enabled to see that. That's when you need a logical analyzer, oscilloscope, and so on. But I won't go into details because Henk is about to explain it. What you can also do when you program something very important is using modules or libraries. I say module or library because in MicroPython, that's modules that are defined externally. That's the beginning of my code. It's explaining what kind of modules I will use. Nearly every time you will need the machine, because if you want to put a pin as an output or as an input, you will need that module. So you will import from the module machine, and you will also very often need time, like the sleep for half a second. There is a module that is specialized to do so, and so I import time sleep. And what I did is I import a NeoPixel on your show. There is a specialized LED that can put any color, but which is quite complex to program. So to avoid that you have to write all the code and all the difficult code that you have to send to actually make the right color to that LED, there are modules that will do it for you in a much more easy way. So instead of writing lines and lines of code, there are modules, and so you import them at the beginning of your code, and then you use them inside your code. For C on C++, that's exactly the same idea, but these are called libraries, which is a set of codes that you can compile into your code and then send to your microcontroller. The idea is exactly the same. That's why I'm just explaining MicroPython and C, C++, but in every language, basically, it's the same idea. So all you have to do is to put the power as an output, and then to say that your NeoPixel, those specialized LED, is on pin 12. For this, I have to check the Qiao schematic, and for the simulation, I put it on the Raspberry Pico pin 12, just to have the same code. And all you do is you define some colors. These are RGB colors, so the amount of red, the amount of green, and the amount of blue. If I put only red, no green, no blue, it means that it will go red. Then I will put only green, then only blue. If you put and green and red, you will have yellow color and so on and so on. And all I have to do now, I just define some colors, and all you have to do is to go through a while loop, and you say for every color which is in my, remember, array, I just define an array in here, which every time a color is 3 numbers. You just fill all the LEDs with this. Here we only have 1, but you can have a strip with a lot of LEDs, and then you send it to the LEDs. And you don't have to know all the details about how sending the signal to the LEDs means. The code will do it for you, because the modules know how to do that. So you just play, and you will go through the LEDs and different colors that you just define here. You see this red, then green, then blue, yellow, turquoise, and then purple. And we go loop again and again, because I put it in a while loop. While loop means that will be forever, and that will be go through all the colors that we have defined. Okay, now that's when everything goes right. What if things goes wrong? I totally on purpose didn't explain why the LED only blink from 1 to 4 in my for loop example. If you go back to the for loop example, I said, where was it? Up here. I said for y in range 5, I would maybe you would have expected to blink 1, 2, 3, 4, 5 times, but that's not what happened. Actually, it goes to 4 times, and then the program stops. But you don't really know why. And so what you can do to understand what's going wrong in your code is just, the very basic thing is just to print things. So I just wrote exactly the same code here, but I print here a hello world just to say, okay, I'm ready. I will start to go in my for loop, and then a goodbye world to say just, okay, now I'm done. And so what's happening in here? And what I do is exactly the same as in the previous code, but I added a print blink I times, which means that it will write actually on your terminal, I blink 0 times, then 1 time, and then 2 times, and then 3 times, and then 4 times. Which actually means that if you thought that here writing for I in range 5 means 1, 2, 3, 4, 5, it wasn't true. It was 0, 1, 2, 3, 4. Which is very common in programming language. You don't start counting from 1, but you start counting from 0. And 0, 1, 2, 3, 4, 4 is indeed 5 times. So it means that the LED will blink 0 times, you just see nothing, and then 1 time, then 2 times, 3 times, and 4 times, and it explains why it went that way. So just using a print lets you already see a lot of things, okay? So you can really see things like that. Of course, the good solution would have been to see the documentation of Python range function that will explain you that starting from 0 until n-1, it will count numbers. Okay, so that's for the very basic of programming. Wait, this is about Ada Lovelace. That's all I just went through. So I already explained, depending on your microcontroller family, you will have to send your program to different ways, but I won't go too much into details. It will just depend on your microcontroller. So just know about it and ask your instructor to explain you how to actually send your code. But Tony and MicroPython is the easiest way to go. Henk, I think that's for you now. Yeah, of course, document your code just to be able to document everything in Fab Academy. Henk, are you there?
Yeah, I'm there. I have to share my screen. It's Can you see my screen?
Yep.
Okay. So I'm going to explain when things go wrong, and it's way more fun because you can play with tools. I said the main principle of debugging hardware is that you don't panic. So at the moment when you start panicking, so everything will go wrong. So that's also what's in this nice XKDC. So you fixing problems that you fixed before and go on and go on. So what you first have to do is try to explain what's going wrong. And then the answer should never be it doesn't work. So in the case of just designed and produced circuit boards, you have to break down the problem into small pieces. Is the board powered? After producing the PCB, did you do a visual check? If you did it, do it again. Are the components soldered correctly? Are the components the right ones? And are they placed correctly on the board? So Nicolas and me, we realized when we were preparing this recitation, that for most of you, this will be hard to understand because we never made a board, we never programmed a board. So maybe do it use this recitation in the video in a couple of weeks. So the video will be online and then you might check it. So the problem is you don't have to jump to conclusions. And so it's easy to assume that the problem is in the most complex part of the system, or even worse. And so you can blame the manufacturer of the components for faulty or misbehaving components. But most often, it's the simplest part of the system. And so in most of the cases, it's a mistake you made. And that's not a problem. So when you try to understand what you did and you were able to fix the problem, so it actually says you are a good engineer. So time pressure can be a factor in jumping to fast conclusions, especially in Fab Academy. So it's better to stay calm and think of a step-by-step approach. Here we come to one of the basics of Fab Academy. So one of the major points, and that's documentation. You really have to write down everything you did. So not only to understand what you just did, but it's also a great way of debugging, and so we come to it later. But once you write everything down, in case you didn't solve your problem with the step you just took, you still can go back. So you have to write down what you did, and it will help you to understand what you did. A good read is this book, so the Pragmatic Programmer. It's a collection of tips to improve the development process in a pragmatic way. And another thing to use is, it's called rubber duck debugging, which means you actually need a rubber duck next to your computer. And it's used a lot in software engineering, but you can also use it in debugging by explaining really how do you say it? Yeah, it's a very good method of debugging code by articulating a problem in spoken and written natural language. You can also use your Fab Academy instructor or your fellow student or friend, but I prefer the duck, the duck doesn't speak back. So what I said, don't panic. It's really important to don't panic because if you start panicking, you're probably gonna cause more problems and the whole system is gonna collapse. So to localize the bug, narrow down the problem. You do this by reproducing the problem first of all. So try to do it and a second time or a third time. Then always first do a visual check. So inspect the circuit. See if all components are soldered correctly. Look at the traces, all the solderings in the components. So it might turn out that you used that you used the wrong component, or that you soldered the component the wrong way around. So keep in mind that the problem might not always be visible. So you're working with SMD components; they're pretty small. So you can use a microscope. So this problem we didn't see without a microscope. There was a tiny piece of space between the legs of a microcontroller and the board itself, so it wasn't soldered properly. The next thing is try to narrow down the problem. So if you have this is the USB part connected to your mouse. So it's probably this is the plus, it goes to a voltage regulator, and then it's gonna power up your board. And so try to look how what is working and what not. And so for instance, with this board, so the first thing you need to do is to program the board. When you are able to program the board, at least this piece and the microcontroller should work. And so if you're able to program the board, you're sure that most of this part is working. When the board is not powered, and so you have to look in these components. This was the programming part I just told. And when you are able to power the board, when you are able to program this little programmer board, but you are not able to program another microcontroller, it should be somewhere between the MCU and the 6 pins that connects the other microcontroller. A very basic tool that you can use is a multimeter. It's a hardware tool. It's pretty cheap and it's handy, and so use it a lot. So you can use it to measure continuity. So you can measure if all the traces you use are connected, but you can also use it to measure that there are no traces connected to each other, so that you have a short on your board. So let's see, you can do parallel measurements. you have to look out for that you disconnect your board from any electronic stuff. And here I do a continuity check of a newly made board. So first, see if the beep is working. Then you are going to check all the traces, all the islands. This one should beep. The others shouldn't. That one is connected. That one is also connected, so that's okay. That one is connected. You can also check, so this is a capacitor. And this is an LED. With the LED you can use continue this measurement. You have to put it on this symbol, and then you can check the direction of the component. And so which side is the VCC and which side is the ground. Let's see, this is it. What we check here is the voltage drop, which means so when you power up a board or when you modify something, in this case also by pressure, I push the button. You see in the beginning, so that the voltage drops. So it drops only a little, so say even 2.9. So in some cases it might drop even further, and this even further might be that it's that the voltage drops in such a way that the microcontroller isn't functioning anymore. So then you have to do something and either on power consumption or on the batteries. These are logic analyzers. This board connected to a logic analyzer, and you see it here. So it's what it does. Let's go back. So you see that I connected some traces to the logic analyzer. And the logic analyzer is capable of reading the digital signals over time. And here I use a program to capture the signals. And so these programs, so you can even translate the signal. So this is a simple serial signal that I traced on a TX and RX. So this is same signal. So you see the bytes on TX and RX and the explanation, the actual ASCII code that you sent. You have all kinds of logic analyzers. So this is very cheap. Oh, can you see it? Verilog 8-channel logic analyzer. It only costs a few dollars. So not more than a few dollars. And it's more than enough to do this Fab Academy. You also have, like this one, it's a 16-channel logic analyzer. Till a couple of years ago, it was also pretty cheap, but now I looked and they are now 60, 70 euros. Or you have these small mini devices, also pretty nice, that you can use as a logic analyzer or an oscilloscope. Then you need good micro hooks to connect the pins to connect to the pins. These are some links to DCKey components pins that are really good. But it's mini I just showed. This is oscilloscope. Oscilloscope. So it displays the electrical signal and shows how those signals change over time. This video, it's showing a blinking LED. The oscilloscope is connected to ground and the LED. The LED is blinking at the interval of 1 second. And these are the hands of Duo. And here you can see that she changed time. You can see that it's blinking every second. Here she looks if the button is functioning, and it's functioning. It's taking too long, so I continue. And then you also have radio communication. A couple of weeks ago, I played with Quentin and Chris with Mestastic. We developed a Xiao LoRa board for Mestastic, and I used those SDR dongles. It's a simple USB to SDR device. SDR means software-defined radio. And with these dongles, they cost about 20 euros, I guess. Or this one is a little bit more expensive. With these one, you can capture everything from a few kilohertz till I think 2 megahertz. And this HRF can even go to 6 gigahertz. So what does it mean, software-defined radio? It means that you can receive and decode the signals with software. So not analog with the radio, but digital. So in here, for instance, you see the Mestastic plate. Yeah, here it comes. This is the Mestastic signal shown by software-defined radio. Flashing your board and what can go wrong. A lot of stuff. And so first, I was looking. Oh, wait, go back. So since I'm a all-time Linux user, so I know my way into the operating system. So when I push in a USB device, so I immediately see on a kernel level what's happening. So there should be equivalents for macOS and for Windows. Actually, I don't know them. So, but maybe it's good to share them in Mattermost. We're probably going to use a lot of shell boards during Fab Academy, and not the SUMDs and the 80 tinies. So this is a SUMD board, and it's programmed with SWD or JTAG. You have to connect it in the right order. But so when we start programming those boards, so we'll come back to that, and probably also your instructor. So this is a UPDI board. It's a better, so it's a UPDI interface between your serial, USB to serial, and your programmer board. And this was what Nicolas already explained. I know my time's up. So this was my last slide. As always, read the fucking manual. And so in the manual, there's everything documented what you need. And so if you don't want to be frustrated, so read the manual and don't panic. Okay, this was the recitation. It's a bit early in Fab Academy, because this week, next week, you're not going to touch next week you're going to touch a microcontroller, so you have to program microcontroller. So it's a bit early, but come back and watch the video and ask questions in Mattermost and to your instructor. That's it. Any questions?
It's normal not to get it directly. It's one of the most difficult part of the Fab Academy if you've never touched electronics before. So don't panic, not repeat it. But it's totally normal. Start small. I don't know if there is no question. If Luciana want to give a last word, and other time's up anyway. But if not, see you on Wednesday. Bye everyone.